I'm Jill Marshall, and I've been asked to speak to you today as an expert in the area of electric circuits. I haven't really studied electric circuits professionally, except the electrical circuits that operate in the atmosphere above our north and south poles. I studied magnetospheric physics, and a lot of that is electric currents that are in the atmosphere. But I have looked at student understanding of electric circuits a good bit. And in what I'm going to be talking about today, a lot of it I learned, and I still rely heavily on the work that was done by the University of Washington Physics Education Group that's led by Lillian McDermott. So many of the things that we know about how students think about circuits come out of that group. When I think about electric circuits, I think it's easiest to interpret them in terms of the electric current. And many students are familiar with the term, they've heard the term electric current, but they haven't really distinguished it from other related terms. For example, what's the difference between electricity and electric current, between voltage and current, power and current? And many students tend to think of these things sort of interchangeably. They haven't been forced in their daily lives to distinguish between the different concepts. And so that's an important thing to get at. What really is current? And we like to have what we call an operational definition of it, so that we can think of it in terms that students can actually see, do, and in some cases feel. So the simplest electric circuit that you could start off with about the fewest number of elements possible, is one where you have a battery, you have some sort of a conductor. This is just a piece of copper wire covered with insulation. And this is a light bulb, and we use a light bulb as the element because if the circuit is working, the light bulb will light up, and that is very useful for people to be able to see the current, which normally would not necessarily be visible to them. So I start off my unit where students are exploring electric circuits, asking them to make a simple circuit that will light the light bulb using these three elements. And this has been done by literally hundreds of thousands of students across the country and over time. And a common thing that students do when when faced with this when faced with this task is they will think, okay, this is the battery, this is like the wall plug where I would plug a light in, and then this is like the wire coming out of the wall, and then somehow I have to attach the light bulb to that wire by plugging it into a socket. So they try something like this, where they've connected the light bulb to the battery, particularly people who have not studied physics at all before. That's often the first thing they try. And as I said, it's perfectly reasonable based on their experience of how you normally turn on a light bulb by just connecting it to some sort of a wire that's connected to the wall. But as you can see, it doesn't work. It doesn't make the light bulb light. The next thing people tend to try, and especially people who have had a physics class or had some experience with circuits, is that they try to make a closed circuit. They know that term, and they do that by connecting the plus and the minus end of the battery, understanding that that will make a complete circuit. Now, you in the video can't see it, but I'm going to put my finger on it, and I can feel it. It's actually not so hot because this battery is about dead, but this warms up, so something definitely happens. You do get a circuit if you just connect the plus and minus ends of the battery. But then, when students try to use such a circuit to light the light bulb, see, it was too hot to hold, what they do is they connect the plus and minus end, and then they attach the light bulb much in the way they did before, where they just bring it into contact with the wire at one place. And this, as you can see, I hope you can see it, well, this doesn't light the light bulb either, if you can see that. And so students are nonplussed because they think they've done what they need to. They've got a complete circuit, and they know the battery's still working because it's now burned their finger twice, but they haven't been able to make the light bulb light up. And that's because they're thinking of current as the stuff that comes out of the battery, and to a certain extent that's right, but they're thinking of it as stuff that's inside the battery that will come out and be used up. And that's actually a reasonable assumption to make because they know batteries do eventually get used up. They die, so they're thinking of the current as whatever's in there, and it comes out it gets used up by the light bulb. And in fact, the current is not the stuff that gets used up. The current is a flow. Much as water current is a flow of water, electrical current is a flow of electrical charge, which we haven't talked about what that is, through the light bulb. So it's not actually just going to the light bulb and being used up, it's got to pass through. And in order for something to pass through, it has to go in and come back out. So that requires connecting to the light bulb in two different places, which when younger children in 4th, 5th, and 6th grade try this, they have no idea what they should do. They just try everything, and most of them are able to happen on this just by chance, actually much quicker than older folks are able to. So if you look at a light bulb, and you look at the metal parts, most people know that it's the metal that conducts electricity, so they are looking for metal parts. The threads on the side of the light bulb are metal, but there's also a little metal tip here at the end. And since it's not as shiny, it looks different. People don't always recognize that that is metal. But these are two connections to the light bulb. It's a way in and a way out. And what's connecting those is actually the filament that lights up. So if I had more fingers, I could show you this more readily. But you can see that I'm holding the one end of the wire against the bottom of the battery, and then one end of the wire is going, the end of the light bulb is attaching the threads, and then I'm attaching the other end of the light bulb to the other end of the battery, and I'm getting it to light up. So I'm hoping you can see that on the camera. So that idea of a flow through the battery is the first thing we'd like students to understand about electrical current. And that's in terms of how circuits operate. We want to look at where that flow is going and how it's how we're able to predict it, how we're able to control it. Now the idea that something gets used up, as I said, that's not a nonsensical idea. That's a perfectly reasonable idea because something does get used up. In fact, energy from the battery gets used up, and before you all are thinking, wait a minute, energy can be neither created nor destroyed, that's true, but it can leave a system. It can come out of the battery and go out into the environment in the form of heat and light. So energy does get used up by the light bulb, but the current is not the same thing as the energy. And I use this model often to illustrate that for students. This is a piece of yarn, and it has old spools that had thread on them at one time on it. And I tell students you can think of the current as the yarn. And what that shows is I pull the current through the spools, and the spools are like the light bulb, and my hands are like the battery. The thread is conserved. In fact, if I pull thread out of this end, thread better go in that side, unless the yarn is being stretched. But yarn doesn't disappear. If it comes out here, if it's coming out here, it has to be going in down here. It's a continuous loop. If it stops moving at one point, if I hold it steady here, I can't move it at the other point. So the current is either continuous all around or it's not moving at all. Now what represents the energy or the battery in this, as I said, is my hands. And eventually I'll get tired, I'll get hungry. If nothing else, I'll get old and die, and we'll stop. The current will stop, just as the energy from the battery can be used up. But it's the energy that was being used up and not the current as it goes around. The current, until it finally dies, is always going to be continuous. And this illustrates another point. As you can see, I had a little trouble pulling when I first started. This battery had trouble getting the current to flow through this resistor because I've got a whole bunch of items on here that represent the light bulb, which we call resistors because they actually resist the flow. They make it harder for me to pull. If I just had one, it's trivial for me to pull. It's much easier, and as you can see, the yarn is moving much faster. I'm getting a much higher current as it goes through. So higher current can be more of it, or it can be the same thing moving faster, just as with water. So in this case, I've got very low resistance. It's easy for me, the same battery, to pull this, and pulling just as hard, I get a much lower current in this case. And you can see that also with light bulbs, except in that case, instead of seeing the yarn move, you can use the brightness of the bulb as a proxy for how much current is going through it. So I've got a system here, and I'm actually going to be using 2 batteries because it's the end of the semester and these batteries are on their last legs. So pay no attention to the fact that they're 2 batteries. Think of it as just one. So I'm attaching, I have a light bulb and I've got the current coming in here. It's going up through the filament and coming out here, and it's going back to the battery, making the complete loop as is necessary for the current to flow. So I'm going to put that in and show you, you can see how bright that is. So that indicates a fair amount of current going through that. Now I'm going to take another bulb, and just as I had many spools here and only one spool here, I'm going to add another light bulb. And the way I'm adding it, we say it's in series because we have one following the other, just in a series. And the current that flows through this bulb has to also flow through that bulb to get back to the battery. There's only one path. So we say that's a series path. Now when I put this, when I attach this, okay, you can see that they're both still lit. The current is flowing continuously, and the first one is no brighter than the second one. It's not using up the current before it gets to the second one. But as you can see, they're dimmer than the one was by itself. So I'm just going to quickly switch back over to that condition so you can compare that. And see, that one is much brighter. And again, what is happening is you're getting more current through the one by itself, just as I got more current by virtue of the yarn moving faster in the demo here. Now, that's not the only way to connect multiple light bulbs. You can also have light bulbs connected in a different fashion, and we're going to call this way in parallel. So I have one bulb connected there, and I think I'm actually going to do it. I think I'm going to actually keep my 2 batteries. And I have one bulb connected over here. And if I put my glasses on, I can see I have the batteries backwards. Sorry. And I can make both of them light up. Now here I have the current coming out of the battery. It can either go this way through this one, or it can go this way through that one. And in fact, both of the bulbs light up, and they are just as bright as the one was when it was by itself. To have the two bulbs. And we call this way of configuring, where current has a choice, we say they're in parallel. You can sort of think of this branch as parallel to that branch, as opposed to series, where the current has only one path, and the current going through one bulb will then have to go through the next bulb. The current that goes through this bulb doesn't ever go through that bulb. And just to show that these are as bright, I'm going to unscrew this one and let you watch what happens to that one. As you can see, it didn't really change. This is how bright it is when it's by itself, and it doesn't get any dimmer when I attach those two. Now that's the opposite of what happened when I've added the bulb in series. That second bulb provided more resistance, and so it lowered the current going through not only it, but also through the first bulb. So the first bulb got dimmer. Here, adding this bulb in parallel didn't change that bulb at all. And in fact, we think of parallel circuits that are in parallel across the battery. In other words, there's not anything between, they connect directly to the two ends of the battery. We think of them as being independent. There is one exception to that. If you have a parallel circuit that involves just a wire. So on this side, I'm going to have the light bulb. And on this side, I'm going to have just a wire. Now, we remember what happened when I tried to put the wire from one end of the battery to the other, and so much current flowed out that it actually got hot, and although I was brave about it, it burned my fingers. So I'm doing essentially the same thing here. I'm joining the, except that I have two batteries, but I'm going to join the negative end straight to the positive end, and let's watch what happens to the battery in this case. I'm sorry, the light bulb in this case. And in fact, as you can see, it goes out. And it didn't just burn out, it went out because I provided what's called a short circuit for these batteries. I provided a way for current, to go straight from one end of the battery to the other without having to go through any resistors. And in that case, even though in a normal parallel circuit that adding this light bulb in parallel didn't steal any of the current from this first bulb, when I do a wire, that wire wants so much current that it literally gets hot. It's more current than the batteries are able to produce. And it ends up taking all the current, or so much of it that there's not enough left to light the bulb. So one way to turn a light bulb off is to short it. That is, to provide a path around it that lets the current bypass the light bulb, if you will. And that's something that you might, as I understand it, need to know for your project. The one last thing that I wanted to talk to you all about is switches. And you are probably familiar with switches from the light switches in your house. The switch that I have here is just a little, it's a double throw switch. You could do it two different ways, but I'm just going to use one half of it. So I'm going to connect, instead of connecting my light bulb straight to the battery, I'm going to connect it to this switch. And when I close the switch, the light bulb comes on, because now I've completed the path. When I open the switch, it turns it off. And so I'm going to leave it as a question for the readers, because I'm not sure how much time I've used up, but think about what would happen if I had a switch in a parallel circuit. And I had a light bulb here, and I had the switch on the other side. How would that affect it? But I think that's all of the primary elements that you're going to be needing to use for your project. Light bulbs and connecting wires, batteries, and switches.